Next up on our agenda is Jonathan Brandenburg of Metecs, presenting a brief description of the Ascent Abort 2 test simulation and resulting telemetry. Metecs is a new sponsor for the Flight Software Workshop this year, and we thank them very much for sponsoring this year's event. Welcome, Jonathan. Floor is yours.
Thank you very much for the introduction, Brandon. Can you hear me and can you see me?
We can.
Very good. So as you noted, my name is Jonathan Brandenburg. By day, I am a flight software engineer with Metecs, and by night, I'm a flight software engineer. I have one of those fortunate opportunities where my hobbies and my work have a great deal of overlap. So certainly exciting time. Next slide, please. As I think I've noted before in a previous introduction, Metecs is a engineering services company based out of Houston. We do flight software, we do multi-body dynamics, we do simulation, we do AR and VR, we do robotics. And what I'm talking about today is primarily that aspect of simulation, specifically the simulation around the Ascent Abort 2 test that was run a couple of years ago. Next slide, please. Oh, yeah, more about how wonderful Metecs is. Think of Metecs. Next slide, please. So this is going to be a short and a focused presentation, admittedly, so we may make up a little more time for our agenda. I'm going to talk a little bit and remind us about the Ascent Abort 2 test. It has been a couple of years, but it does strike me in the gut. I remember watching that video when it came out, and it was truly a moving and exciting video to watch. I'm going to talk a little bit about how the hardware in the loop simulation played in that role. I'm going to at least give you one lesson that was learned with respect to simulations that I hope people can benefit from if they haven't already come across it. And then finally, just a kind of an additional sidebar with respect to simulation and how you can use that telemetry to give you greater insight into the results of your system. Next slide, please. So as you may recall, Ascent Abort 2 test in mid-2019 rather, was designed to test the launch abort system for the Orion craft. And the test article, the capsule on top, was designed to simulate the weight and or the mass and the general volume of the Orion craft. It was not functional at all, as I recall. It was designed for, I think, the drop tests that were done previously, and then taken into this new regime of actually flying. The abort test took place greater than 30-some thousand feet, and I think the importance of that is really the timing. As you may know, this test was designed to abort during max Q, the maximum aerodynamic pressure, often described in popular media when you're watching flights as the greatest stress on the craft. I don't know if that was specifically designed to be the most challenging flight envelope or if it was just a good marker for the launch abort test. And then the latter two notes on this slide talk about speeds. And the speeds, well, first of all, a bit of explanation, because when the expected speed is 850 and then it's greater than 1,000, what does that mean? I just want to make sure that I can clarify that a little bit. The 850 miles per hour, to use imperial units, was when the abort itself was initiated. At that point, the motors lifted the capsule away and necessarily accelerated it away from the launch vehicle. And I want to think about those speeds a little bit. Those are fast. I mean, not in sense of, you know, interplanetary velocities, but fast. And the key point there is that things happen very, very quickly in an abort test or in a launch vehicle failure. So the idea is we wanted to make sure that the system would react extremely fast to the abort signal coming from the launch vehicle. Next slide, please. So at this point, we might have played a video, but in order to ensure that we have a good, consistent, and clean experience for all of our viewers, we're not playing videos from YouTube at this time. But I do encourage you to make a note and look for this video again. It's a short video. It's just a smidge over 2 minutes when I cut it to the part I was interested in. The point here is that it may remind you of that excitement you felt when you first saw this. It truly is an interesting, moving, and impactful experience to watch this abort. So please take a couple of minutes when you have the opportunity and look at that video again. Next slide, please. So let's talk a little more about the hardware in the loop simulation itself. Now, but before that craft actually flew, you might imagine that we wanted to simulate the software and the hardware interactions on the ground. In fact, we wanted to do that many, many, many times. We tested on the ground and simulated many, many different failure scenarios, different timings of the failure, and different aspects of that failure. And we're able to do that without obviously sacrificing a lot of hardware at the time. And thus we had a high degree of confidence that the actual flight abort test was going to be successful. It's certainly nice to see that actually occur. So the Ascent Abort 2 simulation is based upon the TRIC simulation framework. If you're not familiar with the TRIC framework, it is an open source simulation framework that's been made available out of NASA. I've used it a fair amount to simulate some orbital dynamics. I've used it extensively to simulate multi-body dynamics. It's certainly a very powerful tool set. Now, by itself, it doesn't have any models. So it's really more of a framework, really more of a platform that you then build your models on top of. But certainly the TRIC simulation is a key part of, well, in this case, the hardware in the loop simulation. It's based upon the Ramtares simulation, and I had to remember what that was. Ramtares, as I recall, is a trajectory simulation designed for the Orion craft. It's a 6 degree of freedom simulation, and is used to simulate, in this hardware and loop simulation, the motions of the Orion craft throughout that abort sequence. And as you can see on the next bullet point, we actually looked at data for actual flight because we had flown the Orion craft before, and we did have some data on its performance in various drop tests. And so we were able to take that flight data and use it as input into the simulation. And then we were also later able to integrate in the flight computers so that we had more of a hardware in the loop simulation. We did have to create a lot of cables, a lot of harnesses to connect up those flight computers into the simulation environment, but that's part of what a hardware in the loop simulation is. This simulation that was developed for the AA2 does support redundant flight computers, so you actually can have flight computers fail over in this hardware in loop simulation. That is some of the testing we did perform in that simulation to make sure that particular failure mode would be successful. I mentioned earlier that we did have different failure modes, different flight computer failure switchovers, different line break senses, different artificially injected failures, all of these things. And then we were able to display this graphically using Edge, which is based upon Doug. And if you're not familiar with those, Doug is a simulation graphics rendering engine. And Edge is built on top of that and used to simulate some very complex models. I think we've used it fairly heavily to, for example, simulate the ISS and have been able to use that for training and simulation. And then we inject state and read state into that using MREST, which is another component that we've used, RESTful being the key word there, a RESTful interface to be able to allow disparate and distributed components to communicate state back and forth. So a lot of words, but hopefully that gets at least some of the point across. Next slide, please. And now we have the very busy diagram. And really the key point here is you see on the right side of that slide the flight computers that can be redundant. You see on the left side the actual simulation environment, which encloses the trajectory simulation. And it was designed, you can see some switches in this diagram up near the top a little bit that allows us to switch in and out simulated versus real hardware, depending upon exactly what we're going to exercise that day. As I say at the bottom of the slide, there is a lot going on here, and there's a lot of complexity involved in such a robust simulation. Next slide, please. We now get to talk about one of our lessons learned, and my colleague is the one that coined the term AA2 clock bonanza. And what I want to point out here is there are a lot of pieces in this puzzle that keep track of time, that keep track of their progress, that have some sort of tick that they take action on. And each of those O's is a clock. And the real challenge, as you may know, is synchronizing, or at least ensuring that these clocks step forward at a consistent common rate. That turned out to be probably the single biggest challenge of this effort, but was ultimately successful, I'm happy to say. So that takes us through at least the high level of the hardware in the loop simulation. I would love to show you the graphics that resulted from the simulation, but I was unable to pull those together. So we're going to have to use our imagination, I'm afraid, on that point. Next slide, please. So there is one thing that I hope to be able to show you, and that's some of this value that you can get from synchronizing the telemetry from such a flight. What I have, or will have here, I hope in a moment, is a video where we actually took the telemetry from initially the simulation, but later on the actual flight, and this is from the flight. And we actually tied it to a video of the flight. Somebody did a very good job of recording the AA2 actual test on film, on video, I guess. And we were able to use that quite productively to be able to tie the telemetry values. So you can actually see on the video the telemetry step up as the video progresses. I think that's on the next slide, if I'm not mistaken. Let's hope that I'm right. Oh, we're playing it now. There we go. There may be some sound of this. If there is, I'll be quiet. Otherwise, I will try to fill the void. You're getting your countdown. You see our liftoff, and on the top left of the telemetry screens, you're going to see the altitude. You're going to see different thrusts from the engines, specifically the abort engine. And I wish we could hear this, but we can't quite. We'll go ahead and watch it. And on the left there, you're soon going to see the bright flash as the abort engines fire and pull away the capsule. Now, what's interesting is you almost lose the launch vehicle in the flame. But if you look very carefully, you do see that it is indeed being left behind and falling away. And right about here, and there we have the launch abort. You'll see that big spike in the top right when the engines fired and pulled the capsule away. And the video will end shortly because I didn't play the whole thing here, just to show the capsule eventually falling into the ocean because we didn't have parachutes on this particular model. There's the spin, yada, yada, yada. So with that, I'm going to go ahead and go to the next slide. You know, I still get moved watching that video fly. Once again, remind you of Metecs and our skills. In this case, we were talking simulation. I personally have a lot of strength in flight software. We're working in GNC and astrodynamics. I have some colleagues with me today that are heavy into the multi-body dynamics side. Just a good skill set. Next slide, please. And at that, I told you I had a short and focused presentation, so we are ahead of schedule. I'm ready to take questions, if any.
Yeah, thanks so much, Jonathan. We definitely have some time for questions, and let's see if any come in. I'll actually add one. Was there any comparison of the AA2 telemetry to the PA1 abort test that occurred earlier in the program?
That's a fantastic question. I wish I could answer that. The pad abort test and the ascent abort test both were interesting, and they both use the same hardware components. I honestly don't know the answer to that. I apologize. Ask me an easier question next time, Brandon.
Okay. All right. Let's see if anything else comes in.
That's quite all right. It was very much a pleasure speaking to you today. Thank you very much for your time. And I'll turn it back over to you, Brandon.
All right. Thank you so much, Jonathan.